Okay, so we have learned how we can use derivatives to solve harder limits, right? We've tried out these L'Hopital's rule calculations. Well, what else are derivatives good for, right? We spent so long learning how to do derivatives. What makes them a good tool? What new things do they teach us about old functions? So this is the topic for all of chapter 4. Let's start out looking at maximum and minimum values of a function. So lots of different disciplines ask us to optimize things, right? Maybe I want the most amount of power out of an engine. Maybe I want the least amount of friction out of some chemical. Well, these are asking for maximum and minimum values of functions. So we might call these optimization problems. What is the best possible value we could get from a function? Okay. So let's start off from a geometric point of view. Here we have graphed a function in pink. Don't know exactly what the formula of that function is, but it's definitely a function. It passes the vertical line test. Well, I can just see right there that the maximum value of this function is 5. How do I know that? That's the highest bit of pink that I see on this graph. I look over on my y-axis, there is y equals 5. That's the maximum value. The minimum value is going to be right down here at -2. So, it's a pretty easy thing to do if we have a graph to look at. But, I can do derivatives without looking at a graph. Sometimes I'll be asked to work with functions without having a graph of my function. So, in principle, if I did have the formula for some function, how do I find its minimum and maximum values? Well, I need a little bit more terminology here. So we're going to call the largest maximum anywhere on the function the absolute maximum of f. Because notice, like right over here, is this a maximum? This f of 7 equals 0? Well, it's bigger than everything else nearby, but it's not the very biggest thing. Is this point, f of 1 equals 2? Excuse me, yeah. Is that a f of 1 equals 3? Is that a minimum? Well, it's smaller than everything else nearby, but it's not the very smallest. So we do want to distinguish between the absolute maximum and the absolute minimum. Those are the largest, the smallest values anywhere inside the domain of the function. But, maybe we could have some things that at least look bigger than anything else nearby, or smaller than anything else nearby. So here's a slightly better picture of that. What's the very largest point that I see? It's up here. This graph doesn't have its axes labeled, so I don't know exactly what its coordinates are, but I can see that maximum. That is the absolute maximum. And I can see the absolute minimum down over here. But then what about these? Here is a point, x equals b, that I am at least larger than everything else nearby. Here's a point, x equals e, I'm at least larger than everything else nearby. So we would call these local maximums and local minimums, respectively. And, maybe we'd be interested in those too. Maybe we really do want the absolute max, the largest of the large, but we'd at least got to watch out for that relative maximum. Maybe that's a false positive when we are looking for the absolute maximum. So my vocabulary here is that this is the local maximum of the function, the local minimum, and there can actually be more than one, of course. So here's a local minimum, here's another local minimum, here's a third local minimum, and so on. So what we're going to do to find these, surprise, surprise, involves the derivative.